So we need to calculate the rate at which entropy increases. So the rate at which entropy increases. So it's not the change in entropy, it's the rate. So it's going to be the change in entropy is measured in joules per Kelvin. The change in the rate in the change of entropy would be measured in joules per Kelvin per second. So Q over T, which is the heat, rather the energy per second, essentially would be 8.40 calories per second. The higher temperature region will be equal to 225 degrees Celsius or 498 Kelvin, and the lower temperature region will have a temperature of 22 degrees Celsius or 295 Kelvin. We know that delta S is simply going to be delta S sub 1 plus delta S sub 2. So we can say this is equal to negative Q over T sub H. Again, energy is moving away from the hotter source to the cooler source because, of course, thermal energy is transferred from hotter objects to cooler objects. So here will be negative Q over TH. And then the lower temperature region is gaining energy, so it'll be positive Q over T sub L. And we're using Q with no subscripts because the amount of energy that leaves the higher temperature region will be the same amount of energy that is entering the lower temperature region. And we find that this is going to be equal to Q, and then we'll say T divided by L, I apologize, 1 divided by T sub L minus 1 divided by T sub H. And we can actually calculate this. So this will be delta S. However, we need delta S. We need to change in entropy in terms of time. So we'll say delta S divided by T is going to be equal to Q over T, and then again times 1 over T sub L minus 1 over T sub H. And we can find delta, well, we can substitute. So delta S over T is going to equal 8.40 calories per second. And then here we'll have 295 minus 1 over 498. And we're getting delta S over T is going to be equal to 4.86 times 10 to the negative second joules per Kelvin per second. So this will be our final answer. That is the end of the solution. Thank you for watching.